is today. We've been talking a lot about like when this is the temperature and this is how much energy is added. Okay. We've been talking a lot about when you heat up a solid, its temperature goes up, right? But then when it gets to its melting point, whatever that number is, right? Melting point, which all different solids will have a different melting point, right? What's the melting point for water? No, melting point. 32 Fahrenheit, or what Celsius? 0 Celsius. And then all of a sudden it levels off and it doesn't change temperatures for a while it's melting, right? Then after a while, once it's finished melting, there's no more solid left, and it starts to increase its temperature again, right? Then it gets to this other temperature up here at the top, which is called the boiling point, right? So like in this intermediate, like during the time when it's going from here to here, it's a liquid, right? And when it gets to its boiling point, does it keep going up or does it level off again? It levels off again while it's boiling. And if we were able to do this, it's pretty hard to do this with the equipment that we have around here. But if we were able to keep it all contained, keep it all in the container instead of like floating away like a gas, what we would find out is that when it's done boiling and the last of it has boiled away into a gas, the gas would then start to increase in temperature again. Make sense? And then we all know what happens when gases increase in temperature. Like stuff starts to happen with pressure, right? And volume, all those things start to happen. So this is what we've been talking about. Today, we're going to talk about how much energy it takes to go from here to here, or to go from, like, how much energy does it actually take to melt an ice cube? You can actually measure that. Okay? So the first thing is you need to know a couple of units of measure. Okay? The main one that we're going to talk about is joules. Okay? It's spelled like that. 1 joule. I'm going to make sure that I don't write this down wrong here. I think I know what I want to write. Okay, I'm glad I didn't say that. Joule is an amount of energy. Just put amount of energy. Okay? There's also another unit of measure that you'll see talking about an amount of energy, which is a calorie. You heard of those before, right? Yeah. What are calories if you're talking about food? Yeah. It's like, what are calories for you? It's how much, what? How much energy is in your food, right? A different amount of energy. Okay? And then this is just your random useless fact of the day. The calories that we measure when we're talking about food are actually not calories. They're actually kilocalories. And we notate that by saying capital C. 1,000 calories with lowercase c's. Okay? So I just want you to be aware of that. The main one that we're going to use is the joule. In fact, I might not ever give you anything for now that has calories in it, but I just want you to know that that's what that is. You're measuring an amount of energy. Okay? Because that's what's familiar. That's what you'll see around the most. But joules is what we typically talk about in terms of how much energy we're adding to stuff in this situation. Make sense? All right. So we've also done a couple of problems where we talked about if you have, I'll draw a little one of these diagrams. If you have a little sample of something, it heats up really fast, right? But what if you have a bigger sample of something? Like what if you have a giant ice cube? It'll take longer, right? This is time, or else energy added. And this is temperature, right? It'll take longer. The height of each of these things is the same. You see that? This is a bigger sample. Okay, so I want you to notice here that the amount of time it takes is longer. Longer time. Same temperatures, right? Ice will always melt at 0 degrees. Water will always boil at 0 degrees. There's a few things that change that just slightly, like we talked about, like elevation changing it, or adding salt to it, of course, will change that. Those sorts of things make slight changes. But in terms of like the actual temperature of the melting point and the boiling point, they are the same. Okay? So melting and boiling points are the same. Always. Okay? Always the same. So now the next question is, how much energy you think it takes? Let's say we have 1 gram and 10 grams of ice. Let's just say. How much energy do you think it takes to heat up the 10 gram compared to the 1 gram? Twice as much? A teeny bit more? A lot more? What do you think? Well, let's say, well, that's true. But let's say we don't really care about the time. We're just worried about how much energy it takes. Like we could add that much energy really fast, or we could add that much energy really slow. But we're just worried about how much energy it actually takes. Let's just say it takes this one 5 joules. By the way, joule, J stands for joule. Okay? Let's just say it takes 5 joules to get our temperature change to happen. How many joules do you think it'll take to change the 10 joules, or the 10 grams? 50? Why do you think it's 50? Like, it's like the same amount bigger, right? That's pretty good thinking. You're right. That would take 50. You got a bigger sample, you got to have more energy. No surprise there, right? So, here is what you need to know. This is maybe the only time in chemistry where I'll actually give you an actual equation. You ready for it? The equation is this. Q, and I'll tell you what all this stands for in a second. Q equals MC, and then watch this one carefully. This is important scientific lingo. You need to know what this means. Delta T. Okay? So Q is equal to how much energy? M equals the mass in grams, usually. Well, when we do these, this will always be joules and grams. I probably will never give you other units of measure for these. C is a constant, which we'll talk about the constants in just a second, but it's just a number that it always is the same. And delta T, that's how you say it, delta. What is delta, by the way? It's a change. Do you know what is that shape called? Like that letter, what is that? What is that called? It's a triangle, but it's a Greek letter, delta. Like, have you ever seen that like on a sorority or fraternity or something? It's a Greek letter, delta, okay? And it always means change in something. In this case, temperature. All right? Now I'll break down, now that we've got that written down, I'll break down what it all means. All right, so Q is how much energy. So how high up do you need to turn your stove, for example, would be a way to think about that. Okay. The mass would be kind of talking about this idea here, that it takes more energy to heat up something big than it does to heat up something small. And so the mass is a really important thing. A constant, I'm going to go through the constants that we'll have in just a second. But basically a constant is just, we call it a constant because it's a number that's always the same. And scientists have done a lot of experiments on it, and it's always consistent throughout all of the universe, which is always the same. Like an example of a constant might be like the speed of light. Light always goes the same speed. So the speed of light could be a constant. Or gravity, as long as you stay on Earth. Does that make sense? Like there are things that are always the same. So we'll talk about those. And then delta T is the change in temperature. So if we go like from 50 degrees to 70 degrees, delta T would be 20. Make sense? Okay. So here is what you need to know. Here are the constants. All of these constants are only for water. Every substance has a different set of these constants, different numbers, different amounts, and that's just kind of how it is. Okay? So for water, you have to melt or freeze. Either way, you can go either direction. It works the same way. This is called the heat of fusion. Okay? Sometimes you might see it abbreviated HF, just so that you kind of see what that is there. And it takes 334 joules for every 1 gram of the stuff. Make sense? Of the water. Which I guess in this case it would be ice that you're trying to melt or water that you're trying to freeze. It takes 334 joules of energy to melt it, or you gotta take 334 joules away if you want to freeze it. Okay? For 1 gram. By the way, how much is 1 gram? 1 gram of water is 1 milliliter of water. Remember that? If you're looking for a visual on what that looks like, it's a centimeter cubed, or 5 of them make a teaspoon. So if you're looking for what that looks like, okay? This is to boil or to condense. Or did we say condensate? Did we have this argument last time? Condense or condensate, whatever it is, okay? This is called the heat of vaporization. That sounds really important, right? You can probably guess what that abbreviation is. Thank you. Okay. And the number is 2,260 joules for every 1 gram. So does it take more energy to melt, or does it take more energy to boil? More to boil. A lot more, actually, right? Is that a surprise? Kind of makes sense, right? Because how easy is it to melt something? You can add enough energy to melt something just by grabbing your ice cube in your hand, right? Or for goodness sakes, even just by leaving it on the counter in your house, right? Because it doesn't take a lot of energy. But if you want to boil something, it takes a lot more energy. Okay? Next one. There's 4 of these, by the way. This one is called, how do I want to write this? Raising the temperature of water. I'm going to say solid water because I really just want to stress that we're only talking about water here. This is not how you spell the word ice. I-C-E. There you go. Okay. This would not apply if we were talking about any other material. If we were talking about iron or if we were talking about glass, all of these numbers would be different. There are numbers that would go with this, but they would all be different numbers. Okay. This is called the heat capacity. Okay. And it's sometimes abbreviated with a small letter C, which, hey, we did that up there, right? Okay. And the number there is 2.1 joules for every 1 gram for every degree Celsius that we want to change it by. So if we want to go up 1 degree versus going up 10 degrees, that's where that goes. Make sense? Yep. And there's one more. You ready for the last one? This one is raising the temperature of liquid water. This one is also called the heat capacity. Also called C, same thing. And I took up a lot more room to write my slashes there than I probably should have. So I'm going to kind of come down here just so I have more room. The amount of energy it takes to raise the temperature of liquid water is 4.18 joules for every 1 gram for every degree Celsius.
So for like the grams, you would multiply. So if you want to go up 5 degrees Celsius, you multiply the 1 by 5. Okay.
Yep. And the cool thing with these, we're going to do a couple practice ones here in a second, but the cool thing with these is that this equation just like works. So you can just put the numbers in, usually, not always, but usually you're going to solve for the Q. Sometimes you might have to solve for one of the other ones, but usually you're going to solve for the Q. And like you might get asked a question like, how much mass could you warm up if you were doing this other thing? But usually I'll just ask you to solve for the Q. And then the other thing that maybe just like to kind of say in here is that what's the difference between these things here? There's two different units of measure here. Do you see this? Do you see this? Those two are the same, right? And these two are the same in terms of their units of measure, right? So when you're looking at these, this one has the changing in the degrees here, but this one doesn't. Do you know why? Go back up to your graph here. How much does the temperature change when you boil the water? It doesn't. So having a temperature change here when you're talking about melting or freezing or boiling or condensing, it doesn't make sense to even have a temperature change because it stays the same the whole time. It stays at 100. It stays at 0. Right? It doesn't change at all. So when we do these, this is why we don't have to have the temperature change when we're doing these here. Some people actually really prefer to write a different equation. Like I gave you this equation right here, right? I gave you this equation. Some people would actually prefer to write a different equation that would have, like, you could write it this way. Q equals M times H, right? Like HF or HV, either one, whichever one would work, okay? Whichever one you were doing. If that makes you happy to think about it that way, do it that way. But to me, it's easier to just say, oh, I can just use any of those constants, pick the one that I need to use for the situation. If the problem is talking about melting, then I'll pick the one that's for melting. And then if there is a temperature change, I'll put it in. And if there isn't, then I won't put it in. Either way works. Okay? Make sense? Yeah. Oh, that was the arm stretch. So that is the notes. And now we'll do some practice problems. I'll show you one and we'll work on some more together. Got it?